100,000 years ago, up to 1 million humans roamed the Earth. Fast forward 30,000 years when the population dropped. Just a few thousand people may have given rise to all modern humans. Something happened. Something big. Something that changed the course of human development. How did this happen? And does our 21st century civilization face the same terrifying threat? There are more than 6 billion people alive in the world today. In order to adapt to the different conditions across the planet, we've developed a wide variety of physical characteristics. We come in a huge range of colors, shapes, and sizes. But what's really amazing isn't how different we are on the outside, but how similar we all are on the inside. Professor Todd Disotell of New York University studies DNA, a kind of human barcode for our inherited physical characteristics. It's been estimated that there's a difference of only about 0.1% in the genetic information held in the DNA molecule between any two people, however different they may look and wherever in the world they originally come from. We all have more in common with each other than we might have thought.
I find it absolutely fascinating how little genetic diversity there are amongst people throughout the world. You see people with different skin color, head shapes, hair types, and all of those things. Those differences seem to really be skin deep when we get down to the genetics.
In fact, there's less variation in the DNA of all of the people alive on the planet today than in just one troop of chimpanzees in West Africa. The small genetic diversity and our huge population may tell us something important about our prehistoric past. That something happened to erase most of the human DNA record. Something that could have decimated the numbers of our ancestors. It's called a genetic bottleneck, a population collapse that wipes out a large amount of the DNA history. Today, they are commonly seen in endangered species. It's like what happens if you shake a range of colored balls out of a glass container.
Here I have a large variable population represented by the 5 different colored gumballs. If this population shrinks by going through what we call a genetic bottleneck, here actually represented by a real bottle, I end up with a smaller pool with less genetic diversity.
The human DNA record suggests that something may have driven our ancestors to the brink of extinction. The evidence in our genes may also tell us when this happened and how many prehistoric survivors made it through the genetic bottleneck. Scientists estimate the size of human populations from the past using mitochondria, a sort of cellular battery pack that has its own DNA. Mitochondrial DNA is only inherited from the mother and does not combine with genetic information from the father. By starting with the total range of these genes identified in today's population, scientists can track back through the exclusively female line and estimate the number of childbearing women who lived in earlier generations. And the DNA that a child inherits is not always a perfect copy of their parents' DNA. It's a little like photocopying a picture and then photocopying the copy over and over again. Each imperfection moves forward to all the following copies, and over time, the picture can change significantly.
So this is how I mutate after 20 generations of photocopying.
Scientists can estimate the date and human population after a genetic bottleneck by comparing the rate of mutation and the present range of mitochondrial DNA variation.
By looking at the pattern of mitochondrial mutations that we see on the planet today and using the known mutation rate of mitochondria, I can estimate that between 50 and 100,000 years ago, there was only a few thousand individuals that gave rise to the populations that we see on the planet today.
If Dissotel's right, then we all owe our lives to these few thousand survivors. However, there may have been as many as 1 million prehistoric people alive before the start of the genetic bottleneck. Stone tools from more than 100,000 years ago have been found as far apart as Northern Europe and China. But how far had our kind developed by this time? Were any of these creatures really human? The Natural History Museum in London is home to one of the largest ancient fossil collections in the world. Dr. Chris Stringer examines specimens from the collection to investigate how far our ancestors evolved by the time of the earliest predicted start of this population bottleneck. Geneticists estimate that human evolution began about 6 million years ago, when the DNA of chimps in our species first separated. But the earliest signs of distinctly human characteristics appeared several million years later.
By about 2 million years ago, we appear to have the first creatures we could call human. The face is starting to show human features. We've got the beginning of the development of a prominent nose. The base of the skull shows us that these creatures were walking upright, and we've got the appearance of stone tools.
Paleontologists use brain size, traditionally measured from the volume of beads that fit in a skull, as a marker of human development. This 2-million-year-old human had a 600cc brain, much larger than a chimpanzee, but less than half the volume of a modern human. Over the thousands of years that followed, human brain sizes increased. By 100,000 years ago, fossils such as this skull from Israel had modern human dimensions.
Essentially, this is a modern human skull. And it shows us that modern humans had evolved by this time. They may well have appeared, first of all, in Africa as far back as 200,000 years ago.
By then, early humans were creating more sophisticated types of tools to meet different needs.
In this case, this tool was probably used for its scraping surfaces, but we find they're shaping spear points, they're shaping tools probably for working wood, and so we're beginning to get the evolution of specialized technology.
And there are some clues that they were starting to think like us.
Well, we've recently discovered evidence of symbolism from 100,000 years ago. We've got shell beads, so people are using body adornment. They're sending messages to each other, if you like, the beginning of art and creativity, the sort of thing that we find with modern humans.
By 100,000 years ago, before the likely start of this genetic bottleneck, a range of prehistoric people were living across much of the planet, including the genetic line of modern humans. But some scientists believe that these intelligent, adaptable people were about to suffer a cataclysmic drop in numbers. So what apocalyptic event could have driven Stone Age man to the brink of extinction? A massive volcano? A destructive tsunami? Or maybe a devastating asteroid impact? Some scientists believe that Stone Age humans suffered a genetic bottleneck between 50,000 and 100,000 years ago. From a global population of hundreds of thousands, the human race may have been sustained by a small group of only a few thousand people. Until recently, evidence of a catastrophic natural disaster that could have decimated the numbers of our Stone Age ancestors lay hidden in the frozen ice fields of Greenland. Tiny air bubbles are preserved in the Arctic ice. They hold detailed scientific information about the climate from when the water froze. Global temperatures can be estimated from the thickness of the ice layers. Aerosol and dust particles hold information about natural events from that time. Scientists can date all this information. A new sheet of ice is deposited each year, so the annual records pile up one on top of another, like pancakes in a diner. The individual layers are identified from ice cores, long cylinders of ice from below the frozen surface in Greenland that carry thousands of years of environmental data. Professor Greg Zielinski of the University of Maine is a leading expert on the study of the ice core record. In 1993, he made a stunning discovery in this environmental time machine.
As I was investigating the record of the sulfuric acid in the ice core, I noticed about 75,000 years ago that was this very large spike or really very high concentration of sulfate. To have something that big was just so exciting that I wanted to investigate it more.
Zielinski had discovered the highest annual acid reading in the entire 110,000-year record of the Greenland ice core, which points towards a cataclysmic natural disaster.
This large amount of sulfuric acid really only has one potential source, and that would be an extremely large, massive volcanic eruption.
The unprecedented acid discovery in the ice core came from a huge volcano. Major eruptions blast out enormous amounts of gases, including sulfates, which turn into sulfuric acid in the atmosphere. The largest acid cloud of the 20th century came from the 1991 eruption at Mount Pinatubo in the Philippines, which ejected 20 million tons of sulfur dioxide. Acid in the ice core suggests that 75,000 years earlier, an eruption 100 times greater than Mount Pinatubo blasted the Earth. Most active volcanoes lie at the boundaries between the vast tectonic plates that make up the Earth's surface. Which of these seismic hotspots could have generated the record ice core acid reading 75,000 years ago? Could it be Vesuvius, which buried Pompeii and Herculaneum in a sea of hot ash when it erupted in 79 AD? Or Krakatoa, which is said to have generated the largest sound in human history when it erupted in 1883? Or maybe Mount St. Helens, the United States' deadliest volcano, which killed 57 people in 1980. But none of these notorious danger points shows any evidence of volcanic activity on this scale. The most powerful supereruption of the last 2 million years happened in Southeast Asia on the Indonesian island of Sumatra. Lake Toba is an enormous body of water, 60 miles long by 20 miles wide. In 1929, Dutch geologist Van Bemmelen identified this location as a vast caldera. The hole left behind after a massive volcano eruption blasts material into the atmosphere. In fact, Much of this huge crater was formed following a super eruption 75,000 years ago, in line with the timing of the record acid discovery in the ice core. This eruption, 3 times bigger than the last major event at the Yellowstone supervolcano, could be the colossal natural disaster which threatened the future of our kind. The dramatic power of this volcano comes from the chemistry of the rocks deep beneath the surface of the lake. Sumatra lies close to the boundary where the Indo-Australian tectonic plate pushes beneath the Eurasian plate at a rate of about 2 inches per year. The lower plate releases water, causing rock in the plate above it to melt and then rise as low-density magma. At surface level, this melted volcanic rock becomes lava, but it is the potential of magma trapped below ground to hold in gases that creates the explosive power of a volcano. Dr. David Wark of Rensselaer Polytechnic Institute in New York State studies the composition of the magma to understand why the Toba eruption 75,000 years ago was so powerful. He describes the buildup of the liquid rock in the magma chamber as being like filling a bottle with a carbonated drink.
Like magmas, the soda has dissolved bubbles inside of it, dissolved gases. You can see the gases trying to work their way out there.
With bottles of soda, carbon dioxide can move easily through the drink and escape. This is like low viscosity magma, found at volcanoes such as Kilauea in Hawaii, where gases bubble up through the liquid rock, and lava ebbs out slowly at the surface. But in most explosive eruptions, a very sticky form of magma holds in the gases.
So the bubbles are trapped, and when they go explosively. Like dynamite.
The high viscosity or stickier magma at explosive volcanoes like Soufriere Hills in the Caribbean holds in the gas until it escapes in wild eruptions. Magma can expand by up to 600 times during an eruption if enough gas is trapped in the high viscosity melted rock. This is what gives the volcano its explosive power. Wark tests magma from the 75,000-year-old eruption, along with a control sample from a nearby Sumatran volcano, to demonstrate why the Toba event must have been so violent. At 1,300 degrees centigrade, or more than 2,000 degrees Fahrenheit, the control sample melts. Even to the naked eye, the sample from the Toba magma is much more viscous, able to hold in more explosive volcanic gases than the control sample. A powerful microscope highlights holes in the melted Toba material. These are the spaces left behind after the huge volume of gases escaped during the super eruption.
It's the bubbles that are trapped, and they're trapped because of the high viscosity that makes the eruption so explosive.
75,000 years ago, thousands of cubic miles of magma collected under the Sumatran landscape, creating overwhelming pressure on the surface. "200 cubic miles of ash blast out from Toba, covering an area more than 10 times the size of California. Over 2 billion tons of sulfuric acid explode into the atmosphere. This is the biggest eruption modern man has ever experienced. But how could one volcano drive the human race across the face of the planet to the brink of extinction? A massive supereruption about 75,000 years ago on the island of Sumatra could match the timing of a dramatic human genetic bottleneck. From a worldwide population in the hundreds of thousands, our entire race may have been sustained by a small band of just a few thousand. But how could a natural disaster in Southeast Asia threaten human development across other continents? The Toba supereruption would have triggered a series of deadly hazards. Close to the volcano, the effects would have been apocalyptic. Imagine pyroclastic flows, superheated avalanches of volcanic material. They wipe out an area of more than 7,000 square miles of Sumatra. They vaporize anyone in their path. They extinguish all signs of life across the width of this vast island. An eruptive column up to 50 miles high ejected more than 200 cubic miles of ash into the atmosphere. We have experienced the lethal consequences of volcanic ash in recent times. When Mount Pinatubo in the Philippines erupted in 1991, the column reached a height of about 22 miles. Dennis Shows was a serviceman stationed at the nearby U.S. Air Base.
You could see the volcano erupt because it looked like a cloud of ash rolling over the sky. Looks like something out of a movie.
Unfortunately, this was a horror show without a happy ending.
Everything was just gritty everywhere. All the branches were gone. All the vegetation was just covered and coated, and everything is just gone.
The Pinatubo eruption killed 320 people. Volcanic ash caused most of the deaths. But here, volcanologists identified the threat early. A mass evacuation saved up to 20,000 lives. At Toba, there would have been no warning system, and the supereruption 75,000 years ago ejected 200 times more volcanic debris than Pinatubo. The ash cloud would have covered an area in excess of 1 million square miles. Now, a new archaeological find gives unique insight into the impact of this terrible downpour on Stone Age societies. In the year 2000, a layer of Toba ash about 4 yards deep was identified in southern India by Dr. Michael Petraglia of the Leverhulme Center at the University of Cambridge.
It is a spectacular deposit, very thick sequence with archaeology associated with it. It's a one-of-a-kind find.
You're pretty far down.
In the immediate aftermath of the eruption, nearly 6 inches of ash fell on southern India. The first threat to the Stone Age hunter-gatherers would have come from breathing in this fine powder.
These particles are like little glass shards. And these glass shards, if they get into your lungs, they can cause all sorts of damage.
This deadly dust would have poisoned the drinking water and made fertile fields barren. When carried by the rain from the annual monsoons, the dust built up to 4 yards deep is found at Petraglia's site. Archaeologists have discovered no human remains under the Toba ash layer. A collection of Stone Age tools is the only surviving evidence of the society that existed here before the supereruption.
Well, what's so interesting is that we find these in great abundance below the ash. But once the ash came, it seems that those populations using these stone tools were no longer there.
Volcanic debris from the Toba eruption threatened hunter-gatherer societies over more than 1 million square miles. But long after the ash cloud scattered, Stone Age survivors across the globe faced a second threat. An acid cloud, created by the 2 billion tons of sulfates blasted out by the supervolcano. acid droplets in the stratosphere would have blocked out most of the sunlight, triggering a global 6-year volcanic winter. Professor Howard Griffiths of Cambridge University investigates the impact of this sudden climate change on plant life.
What our experiments have done have mimicked the effects that we'd expect to see following that volcanic eruption. We have reduced the light intensity, we've reduced the temperature, and we've reduced the water availability for plant growth.
Acid from the Toba eruption cut out up to 90% of available sunlight. But plants use energy from the sun to grow, a process called photosynthesis. Griffiths investigates the impact on his test samples of dropping to the lowest light levels of the volcanic winter.
What we've got here is that the leaf has now stopped photosynthesizing altogether, so growth would stop.
The low sunlight levels caused by the Toba eruption could completely halt plant growth, and the acid cloud reduced global temperatures by as much as 30 degrees Fahrenheit. Griffiths applied this additional trauma to the experimental plants over a period of 2 weeks.
Here you can see there's some immediate effects with rather yellow gaps indicating a loss of photosynthetic activity. The low temperatures has really reduced the potential of this plant for growth.
To make matters worse, the volcanic winter would have triggered a major drop in rainfall in some areas. A microscopic exam of test subjects that suffered all these environmental changes suggests that the combination of reduced sunlight, temperatures, and rainfall would have had a deadly effect on vegetation after the Toba eruption.
What our experiments have shown is that the combined stresses that were predicted to have accompanied the Toba eruption will have the effect of basically deforesting and defoliating the entire environment.
The super eruption 75,000 years ago caused a terrible volcanic winter that laid vegetation across the planet to waste. This could have decimated most present-day populations. But there were survivors, and it's their descendants who went on to make the world we know today. So who were these people, and how might they have survived in the harsh aftermath of the most powerful volcano of the last 2 million years? Some scientists believe that a human bottleneck left a population of only a few thousand people to continue our species. They link this to a deadly super eruption about 75,000 years ago at Lake Toba on the Indonesian island of Sumatra. So where are these survivors of this global catastrophe? Geneticists can trace the movement of early humans by comparing DNA variations in different parts of the world. The area with the greatest genetic diversity is the most likely origin of communities with lesser DNA diversity. Professor Todd Disotell of New York University uses a deck of cards to explain.
If I take a full deck of cards and I shuffle it and then I deal them out, there'll be hearts, there'll be clubs, there'll be spades, there'll be diamonds. Then if I only take a small group of cards, let's say they're all red, no matter how often I shuffle them, all of the hands that I deal will always be red. So the greatest diversity we'll ever find is always from the founding population, in this case, the full deck of cards.
This isolates the most likely source of modern humanity to the area with the greatest genetic differences, East Africa. In fact, there's likely to be more diversity between the DNA of 2 neighbors in one village in East Africa than between a person of Southeast Asian descent and a person of Northern European descent.
The diversity that we see basically around the planet seems to be traced back to East Africa.
Many experts believe that our entire 6 billion population came from a cluster of only a few thousand people from East Africa about 60,000 years ago. But there's archaeological evidence of up to 1 million humans living across much of the globe tens of thousands of years earlier. Something seems to have happened to halt human development across most of the inhabited world in a prehistoric game of risk. The Toba supereruption 75,000 years ago caused a destructive global volcanic winter. A small band of East African survivors of this apocalyptic natural disaster may have sustained the entire human race. Professor Stanley Ambrose of the University of Illinois believes that the supereruption did trigger a genetic bottleneck. And he has a theory on how a small group of East African hunter-gatherers adapted their behavior to survive the harsh aftermath of the Toba volcano.
I think Toba changed the course of human history by forcing people to become cooperators as opposed to selfish defenders of their small territories.
Ambrose believes that a few thousand of our prehistoric ancestors survived the genetic bottleneck by learning to work together, building support networks and developing more advanced forms of communication. He bases his theory about the movement between Stone Age communities on the materials used to produce prehistoric tools in Kenya, and especially on a type of volcanic glass formed from lava called obsidian.
Things that made obsidian so valuable was that it was so sharp, like broken glass, which is what it is, that you could actually shave yourself with it.
Razor-sharp tools were precious possessions in Stone Age times. People would have gone to great lengths to find obsidian. It's possible to discover which volcano the obsidian originally came from. Archaeologists used this information to track movement across the prehistoric landscape. Ambrose discovered that the tool-making materials at sites from before the Toba eruption were almost all sourced locally. The stone came from inside the boundaries of the hunter-gatherer community that lived there, suggesting that there was little communication between groups. A volcanic winter triggered by the supereruption, when temperatures in Africa dropped by up to 30 degrees Fahrenheit, rainfall fell by up to 90%, and much of the vegetation died, seems to have changed this. At archaeological digs from after Toba, like this one near Ntuka, 60 miles west of Nairobi, most of the tools are made from obsidian, which Stone Age settlers had carried much greater distances from territories inhabited by other groups.
Well, there's a piece of obsidian. It's likely to have come from about 70 miles away. When I find obsidian out here, it doesn't just mean to me a stone tool, it symbolizes relationships, the ability to get across a territory.
The movement of the obsidian suggests that in the bleak aftermath of the supereruption, people traveled long distances in search of scarce resources. But as Ambrose retraces the route of our Stone Age ancestors to the obsidian source at Crater Lake Quarry, he demonstrates that this is a tough area to cross.
Driving around the African landscape is difficult enough. Doing it on foot with wild animals must have been a really incredible challenge for these people.
An experiment at Kenya's Hell's Gate National Park shows how rigorous the 70-mile journey to the obsidian source would have been on foot. Daniel Shaw is a fit, healthy guide from a nearby Maasai village.
The blood pressure is 100/60.
He starts at dawn from a local landmark, Fisher's Tower, and attempts to walk as many miles as he can through this tough terrain before returning at sunset. Shaw covers a fraction of the 70 miles separating the Stone Age settlement and Crater Lake Quarry over the course of an exhausting 12-hour trek.
He's walked 14.88 miles.
It could have taken prehistoric humans days to get to the obsidian source, crossing the territories of other hunter-gatherer groups on the way.
They would have to either avoid encounters with the people who lived in this area or have very good relationships with them. They probably preferred to have good relationships because I don't think any rock is worth your life.
Ambrose believes the tough East African terrain would have forced people to cooperate with their neighbors as they hunted high-grade tool-making materials from obsidian sources such as Crater Lake Quarry.
I think this is a great place to come and collect obsidian if you're a Stone Age person because you can pick and choose the pieces you like very easily. So it's sort of like a supermarket where you can just come and pick what you'd like off the shelves.
The sophisticated tools that were made from high-quality obsidian would have helped the ancient Africans to survive in the barren post-Toba landscape. But Ambrose believes the communication skills people learned while collecting tool-making materials would prove to be more significant over the centuries that followed.
The fact that people came from such long distances implies a new set of skills for negotiating, traveling across people's territories. I think that was the last step in the development of language.
He believes our ancestors' new skills developed in the tough climate after the Toba eruption changed the course of human evolution across the planet.
Toba probably ultimately allowed people to get out of Africa and populate the rest of the world. This was just the beginning of a revolution that I think has continued.
If the Toba theory's correct, then the 6 billion people alive today are descendants of a group of just a few thousand people from equatorial Africa who learned an entire set of new skills to survive the horrifying aftermath of this super eruption. So are there any lessons for us living in the 21st century? If the Toba supervolcano made our modern civilization, could it also destroy it? 75,000 years ago, the most powerful supervolcano modern man has ever experienced erupted in Indonesia. It may have even driven the human race to the brink of extinction. Lake Toba, on the island of Sumatra, formed in the crater left behind after 200 cubic miles of ash blasted into the atmosphere. Today, this is a peaceful place, occupied by fishing communities and visited by tourists curious about this vast lake and the hot springs that are a rare reminder of its volcanic past. But this calm could be shattered at any moment in this region of high seismic activity.
15, 20 feet tall. Easy.
December 2004. An earthquake in the Indian Ocean launches the deadliest tsunami in history, raising fears of new volcanic activity in Indonesia. The vast readjustment in the Earth's crust which triggered this tragic series of events happened on the Sumatran Fault, part of the same geological system that caused the super eruption on the island 75,000 years earlier. Many scientists believe there's a direct link between earthquake activity and volcanic activity. But for Toba to erupt, it would need to have a large volume of magma already built up under the surface. Professor Rob McCaffrey of Rensselaer Polytechnic Institute in New York State made a study of volcanic activity beneath Lake Toba in 2001. A simple experiment in the college grounds shows how he used sound waves to understand the subterranean geology in Sumatra. Students position a series of sensors at equal distances from a source of sound waves, in this case a hammer.
There you go.
The sound waves from the hammer blow move through different materials at different speeds. So even though the sensors are the same distance away, it reaches some of them more quickly.
There's a good one. Waves that travel through the walkways arrived sooner than the waves that travel through the soil underneath the grass. That's because the walkways are much more consolidated.
So by analyzing sound waves at different points, scientists can create a picture of the geological features they have passed through. McCaffrey sets up sensors around Lake Toba to measure the sound waves generated by low-level earthquakes. His readings reveal an immense volcanic system hidden deep beneath the lake.
Our tomography results suggest that there are two separate chambers, a large one in the south and a smaller one in the north.
And there's alarm. There are signs of new activity at Toba.
If we're interpreting these things correctly, it looks like there is magma feeding directly into the chamber and rejuvenating the volcano today.
There's still volcanic activity at the site of the largest eruption of the last 2 million years. To determine if a major new eruption's looming, experts look for signs of movement in the ground above the magma chamber. In 1993, McCaffrey took GPS positioning measurements all around Toba. In 2001, he returned to the site to look for surface changes.
To our surprise, things just weren't moving at all. We could measure to within a 1/16 of an inch, and at that level, we didn't see any movement at all. Well, I would say that I don't expect anything catastrophic to happen at Toba, within my lifetime anyway.
Toba may be safe for the near future, but what about the dozens of other ancient supervolcano sites, including the most famous at Yellowstone National Park? At Yellowstone, there's clear evidence of a volcanic past in the rugged landscape. And a series of geysers, fumaroles, and hot springs reveal continuing subterranean activity. Enough to have raised fears of a new super eruption brewing beneath the surface here. The problem is that we have no record of exactly what the warning signs are for these catastrophic events. This is one of the greatest concerns for Professor Bill McGuire, director of the Benfield Hazard Research Center at University College London.
The trouble with super eruptions is that we've never experienced one in modern times, so we don't know exactly what we will see before one of these eruptions. We may get months of warning, we may only get weeks, we may only get days.
It's unknown where the next super eruption's likely to happen.
They may occur where there hasn't been any eruption before. So magma may have been accumulating over the last few hundred years, and the first we'll know about it is when that magma breaks the surface and we get one of these huge eruptions.
And super eruptions like Toba are on a completely different scale from the volcanoes we have experienced in modern times, such as Mount Serrat in the Caribbean, Etna in Sicily, or Mount Pinatubo in the Philippines.
If this ball represents the volume of material ejected by Pinatubo, which was one of the biggest eruptions of the 20th century, then this basketball represents the amount of material ejected by the Toba eruption. Now, Pinatubo actually cooled things down by maybe ½ degree. It actually slowed down global warming. So you can imagine what an eruption of this size would do to the global climate.
Our modern infrastructure is not designed to handle a Toba-level climate change, like temperature drops of up to 30 degrees Fahrenheit or 90% rainfall reductions. A modern supervolcano could be 1,000 times more devastating than the worst natural disasters on record.
I think the next super eruption will kill perhaps 1 billion people through starvation. It will bring the global economy to the edge of complete collapse, and it will be the greatest disaster that our civilization ever had to cope with.
The awesome dimensions of the Toba caldera are a somber reminder of the power of nature. The super eruption here 75,000 years ago may have threatened the very future of the human race. The chances of a similar apocalyptic event in the 21st century are low. Maybe just 1 in 500. But the consequences could be just as devastating.